Yeah, just a short introduction. Tobias not able to come, so we both coordinate this project. Started as FUSIMO project in 2010. We have received nearly 9 million euro for this to tackle the key problem of applying MRI-guided focus ultrasound on liver. And the current problem is that this can only be done under specific restriction, takes a long time because it requires apnea, and there's only very limited access to the liver. We show here our concept already, which is the Insightec conformal bone system placed on top of the patient, which would allow much more access to the liver, but still we are restricted by the motion of the liver and by the rib cage. With beamforming, which this CBS allows, and we have added additional programming, it's possible to follow the liver via the MRI 4D tracking. It's also possible to avoid damage of the rib cage by blinding out elements. There will be an improved, strengthened transducer available probably next year, and we're heading towards first and then next year. Now the technical part will be covered by Sabrina because it's a very strong software-based, programming-based project where she knows much more than I know. So Sabrina, please. If you have any clinical question, you can ask me. Thanks.
Okay, thank you. Okay, so this is the consortium. It consists of 11 partners from 7 countries around Europe. Okay, so Andreas also already mentioned our concept. So we have the TRANS-FUSIMO system, which contains a HIFU device and also an MRI device. So what is new in this project is that we have a treatment software called TRANS-FUSIMO treatment software, which is able to control both of these systems via the real-time APIs of the system. Okay, so but how do we want to do this? Okay, so you all know that FUS is an image-guided therapy, meaning that we have to acquire images, to do quantitative image processing on these images, and to act accordingly. So on this slide, we are having the time on the x-axis and the motion of the liver shown in the graph. Okay, so now we have different time points where we acquire the images, which takes also a certain time. Afterwards, we have to control the FUS device according to the new images which we have received before. In between, however, we have to perform some computations which allow us to predict the next position of the liver in this small range of time, which is around 250 milliseconds. The main problem then is that the uncertainty is growing with the prediction time. Yeah, so the longer you have to predict in the future, the larger is the error you are doing. Okay, and this is this graphic showing. So our system now contains the following parts. We have a motion tracking, so a real-time motion tracking. We have a motion prediction, a beam steering, of course, a temperature monitoring, and also maybe in future versions, the risk prediction. Okay, telling something about the motion tracking and modeling. So prior to the therapy, we are receiving 3D breath-hold images of the patient, where we can delineate structures on and plan approaches. Then during therapy, we are receiving motion tracking information via the MR or ultrasound. You will get to know more about this in the next talk. This information about the real-time tracking is fed into an offline motion model, which we have received earlier. And then we are receiving a motion prediction, which is patient-specific. And this one we are using to adapt our focal spot to the next position. Okay, concerning the ultrasound modeling and beam steering, we have an offline atlas for the ultrasound model with an improved hybrid angular spectrum, and this contains also pre-computations with discrete focus locations. Okay, so in the real-time therapy, we synthesize from these pre-computations and adjust to actual transducer settings and material parameters. So this is, for example, important if we want to focus through the rib cage. Yeah, then we have to shut off some elements, and then this is of use. And furthermore, we have to monitor the temperature in the moving organ, since the patient is breathing all the time. And therefore, we are using a multi-baseline MR thermometry algorithm. And what we can do, since we are only having on a single slice the temperature monitoring, we can use also a temperature simulation to have a larger volume of temperature information. And this also can be used for a risk prediction in the next version of the software. Okay, so having said this, the main goal of TRANS-FUSIMO is to translate everything I said before into the clinics. So we are also concerned with the preclinical validation according to ISO 13485. So the specifications are listed here, which we are testing against. We have a first-in-pig experiment performed on March 31st in this year, and the software is almost ready to go into the animal study. Okay, so here are two screenshots of the setup for the validation of the models. We can see the phantom, which is moved by a robotic arm to mimic the motion of the patient, or the breathing motion of the liver of the patient. So this is our timeline. So currently we are having feature freeze of the software. Then we are trying to finish the validation as soon as possible and move on to the animal trial. And hopefully have also a human trial at the end of the project. So the project ends at the end of 2018. Okay, and yeah, thank you for your attention, and thank you to the TRANS-FUSIMO team and the funding from the European Commission and the other funds. Thank you.
Do we have any one quick question from the audience regarding this project? Over here.
Yeah, very good question. So we're heading towards conscious sedation. Otherwise, it would be, as it still is, a very long-term and awkward procedure with anesthesiologists involved, and this is the ultimate goal. We may start under general anesthesia on the first-in-man for security reasons.
Thank you very much.